Hi there, everyone. We're moving on to question number 3 now. So let's take a look. What we have here is Sloan is trying to high jump and leaves the ground with a vertical velocity of 4.2 meters per second. What is the peak height? I was just looking at the first one. What is the peak height of Sloan's feet will attain? Okay. So there's a few things here that we can assume. One, instantly this should start sounding some alarms in your head, or feeling and looking familiar as far as being a projectile motion question, right? So we have something or someone jumping or flying through the air. Okay. So we draw a picture of that. Let's do about here. Okay. So we only know the vertical velocity, and if you think back to projectile motion, whenever we're dealing with height, what we want to usually isolate or figure out is vertical velocity. Okay. So horizontal velocity doesn't matter when we're dealing with height, right? We separate the x and the y axes and their influences on motion. Okay. So this is great. Already we have a sense that we're being given the information we need right from the get-go. Always great to draw a picture, get orientated with our coordinate system, and then move forward from there. So let's continue to do that. So here we have our starting point. Let's say the ground. We know that Sloan is going to try to jump up, and that vertical y component of the velocity is 4.2 meters per second, and that as they go through the air, whatever that happens to be like, again, trying to get over the high jump bar, that's some height up. We're gonna look for the peak height of Sloan's feet. So while it might be a little tricky to discern, because usually with a high jump, the people flop over the high jump bar. It's called the full sin flop, but we can assume that wherever they happen to jump over, that at the peak height of this parabola, remember parabolic flight paths is just that curved flight path, that their center of mass and their body follows that same path. So ultimately the height at which any part of their body occurs at is where their feet are going to end up. That's the highest point it's going to be. So we make an assumption here, again, where Sloan's feet is going to reach at the height of any part of their body as they go up to the top and over the bar. Okay, so here's kind of our system. Again, the mat, sorry, just to be clear, is going to be over here somewhere, and they're going to flop down on there. But that's not really what the question A is asking for. Again, it just wants the peak height. Okay, just the peak height. So again, the apex of wherever they're jumping to with their vertical velocity of 4.2 meters per second. Okay, wow, what do we know? Again, just to be clear, we only really know their vertical velocity. Right. So we can say equals velocity of y, because remember up and down is y, and we can say I. Okay. Just as a reminder, anything in subscript is usually more descriptive. So any of the small letters you'll see down on the right, just to help you track along with what variables belong where. Because again, we could have velocity on the x, that's its initial. We could have a velocity on the x-axis, that's a final. We could have, same with the y-axis, we could also have a final there, okay? So again, they're just help label. They're like label makers, okay, just so you can track along. Great. So again, we got all the information we need here. What we're going to do is mosey on over to our question again. Okay, and go to our equation sheet. So here we are at the equation sheet. Now, again, looking here, they're generally grouped together in various chapters in order. So here we know is kind of our kinematic equations for linear or one-dimensional sort of stuff. We get into our angular, two-dimensional things here. Now, remember, projectile motion has two dimensions, the x and the y. So this is probably where we're going to stay. Just as a reminder, this is our angular stuff over here, generally speaking. Okay. So let's get back over here. Okay, well, do we have any information about angles? No. Does it want us to solve anything for that? No. So we can keep moving forward from here. Okay. And we'll look down here. Okay, we got some y, changes the displacement. Okay, so now we're talking. That's a possibility. What else do we got? That one doesn't really have any variable as far as change of displacement on the x or the y-axis, so we'll skip that. This one does, so maybe we could use that one. This one does for sure, and that one does not have any change in y or x-axis. Okay, so we really have, let's go back and review. We have one option here, we have another option here, and potentially our last option here. Okay, well, and I'll show you after the question if you're interested, but this is really just a rearrangement of this equation here. Okay, so all we've done is given you a shorter version of this longer equation if and when at some point in time there's zero velocity and you're trying to find the change in displacement on the y-axis. Okay, so this has just been simplified for us and rearranged so that we can just solve for y without having to do any of that math, any of that rearranging. Great, yeah, that's really handy to have. So let's take a little look at that and how that looks. Let's plot that down. So delta y equals minus v squared initial divided by 2. Now it says 2a on your equation sheet, but as you recall, when we're dealing with free fall or projectile motions and stuff, that acceleration is actually just gravity. Okay, so you can use those interchangeably as long as your system and the question requires that or applies that situation. Okay, now I put brackets around the velocity initial before I squared it because we want to make sure that negative sign stays there. Okay, I'm going to come back to that, but that's just a little bit of foreshadowing to keep in mind. Okay, great, rocking along. So let's put in what we know. So let's see, our velocity initial on the y-axis we said was 4.2 meters per second, and that's squared, all of that term. And then we're going to divide that by 2 times gravity, which is a negative 9.81. I'm going to treat that all as one calculation there. Okay, so as we go through this again, we want to calculate the squared component without the negative sign in there. So what that gives us is a negative calculated 17.64, okay, over top of a negative, again that's all one term, 19.6. Okay, and again this is because the negative on the acceleration of gravity. Okay, so last but not least, once we divide 17.64 by 19.6, both being negative, we get a positive. I'm actually gonna punch that into my calculator now. Oh, let's see, it is, I think I remember doing this before, so it's 0.9 meters, or it's like 889, and then you round up. Okay, we're just making that change now. on the answer sheet for you. Okay, so there we go. So at the peak, we've gone to 0.9 meters for Sloan. Great. Okay, so that's our first question done. That's our answer. Don't forget those units, right? So the vertical displacement, so the change between point A and the apex of that jump, again, delta y equals 0.9 meters. Okay? Almost 1 meter. Pretty high jump. Okay. Awesome. Moving forward, let's check out the next question. What are we being asked here? So now we're being asked how much time goes by before Sloan reaches the apex. Okay. All right. So a few ways we can do this. But let's make an assumption for simplicity's sake that we actually didn't solve for that yet. Or maybe in, say, like a test or an exam situation you had, but maybe you're feeling unsure about that. We can still figure out the time to the apex without using that. Now, if you wanted to return to a different kinematic equation and include that, or maybe you did that for yourself when you solved this problem, that's okay. Remember, there's a few different avenues to get here based off of the other equations. I'll show you the rearrangement at the end of this if you wanted to stick around for that. But yeah, we can do it without. So again, we're going to go back and look at our equation sheet. We're going to stick around the same area because we're still within projectile motion. And we're looking now for something with time. So again, as we go through these, okay, there's time, gravity, great. So I could use that one. There's time in this one, change of time, gravity, plus initial and final velocities, which we do know. Remember that our initial velocity is given to us on the takeoff, and the final velocity at an apex is 0. Okay, so let's check in on this because this is a pretty important aspect to consider. Okay, so if I take a look at some sort of object, I'll erase this after, but so here's our classic parabolic projectile motion path here. So if you recall, no matter where you're at on that parabola or parabolic curve, you're always going to have a 8.1 or 9.81 acceleration, okay? And I say negative because that means downward, okay? Negative. This is, again, just how we're setting it up. So alternatively, upwards would be positive on our coordinate system here for this projectile motion, okay? So what we can do with that is just recall that from here we have some sort of initial velocity, and we're only going to consider the vertical component. Remember that if I have something that is at an angle, that I can break that down into the vertical component, so the y-axis vector of velocity, and the x. Just using my tip to tail addition strategy with my vectors there. Okay, so the green is how the actual velocity of the object is. The red and the orange were ones that we created that add up to equal the green. Okay, so again, going back to what we're actually focusing on in this sort of motion, we're only looking for at the red velocity. Okay, so over time, our initial red velocity is going to be here, but then as we go along, it's going to get a little bit less, till right here at the top it's 0. Okay, vertical velocity is 0. And the reason all of that is happening is that at every moment along the way, acceleration is working against it. So it's decelerating the vertical velocity, decelerating the vertical velocity, decelerating the vertical velocity. Again, it's acting in an opposite direction because it's minus to whatever the positive velocity is right out of the gate, right here. Ooh, I shouldn't do an arrow there. Okay. Now, just as a quick reminder, on the way back down, we're going to get some negative that's going to be continued to be accelerated in that direction by gravity. And then same, more time is going to act on that, and we're going to get more velocity in the negative direction. And again, we're going to get more, even more velocity towards the end, so that it actually equals, if they're at the same height, they're going to equal. So this arrow, if I flipped it upside down, would be this, the exact same height there. Okay, so we just kind of had ourselves situated again as far as how the velocity changes direction, even though acceleration throughout parabolic motion does not. But the other thing too, last part here, is velocity then on this side becomes negative. Okay, so this is just a little bit of a review. It's not specifically going to apply to these questions, in the sense that we're not necessarily going to be finding some value over here. We're going to be looking for how much time it takes to reach the apex. Okay, so where velocity equals 0, that still doesn't mean it's not moving. It's just instantaneously 0 velocity in any particular direction. Again, because acceleration has slowed down the vertical velocity to be 0, and then is just before it starts going to negative velocity. Okay. So how much time does it go from here to take to get up to there? Okay, at the apex, right there. Okay. That's what we're going to find out. So, to do so, let's get rid of all of this. Maybe we can make it smaller. Great. Oh, almost worked. Let's try one more time. No, not going to work. Okay. Instead of minimizing, we'll get rid of it. We might see this again later. Cut it. Great. All right, now from a clean slate, let's return to our equation sheet with this question in mind. So we know we're looking for time. Again, like I said, there's 1, 2, 3 of our equations here to deal with projectile motion that has time in it. So which one do we use? Well, ultimately, if you're only dealing with things to the apex, we have 2 equations that usually deal with that, or free fall motion. Okay. Now the reason for this is, again, this is just this equation rearranged and pre-solved for us. So this is our easier go-to. Okay, we have t. Again, we're only going to the halfway point, so we know this is going to be good. It's going to give us the answer we want. So this is like halfway in projectile motion, these two, or free fall. Okay. So great, we have something rearranged and condensed for us that solves for t. So let's use that one. Okay, t equals negative initial velocity on the y-axis. I should really, for absolute completeness, do something like that. And that's over top of our acceleration, which again, when we're dealing with projectile movement, something free falling through the air, whatever, only one thing acting on it, it's going to be gravity as the acceleration acting on it. So we can say g. Okay, great. Let's keep filling in what we know. So that also equals our vertical velocity, again, initial. So that's negative 4.2 meters per second, and that's going to be over top of a negative 9.81 meters per second squared. And again, just as a reminder, our acceleration, meters per second squared, is essentially equivalent to saying meters per second per second. And the reason that has significance is, if you think of meters per second, that's velocity, and seconds is time. Well, that right there is your formula for acceleration, velocity over time. So literally the units of acceleration tells you the formula for it. Pretty cool, huh? Okay. That was a side tangent. Let's get back on task. Just trying to tie in all the concepts for you. So here we are. If we actually calculate these numbers, I think the one in your answer key was just a little off because it used 0.4. I'll update that as soon as I can. Or, yeah, 4.5. So we'll update that here with 4.2. Negative divided by 9.81. Negative equals. So the answer we get, yeah, is going to be a little bit less, but more or less the same. So the full number would be something like that, and that's of course in time, so that's seconds. And rounding up just to one decimal place, just be 0.4 seconds for you. Okay, great. So again, that's how much time it'll take to get to the top of this parabolic curve on this high jump that Sloan is doing here.